discuss naive Bayes classifier. Naive Bayes classifier. This naive Bayes classifier uses Bayes theorem extensively. Bayes theorem. So what is Bayes theorem? Bayes theorem can be stated like this: probability of A given B is equal to probability of A into probability of B given A divided by probability of B. So that is Bayes theorem. We have proved this Bayes theorem in one of the earlier videos. So what is the problem statement in naive Bayes then? What does naive Bayes classifier does? So we are given k classes C1, C2 up to, let's say, Ck. We are given these classes, and also we are given a data point x. We are given this data point x. So the question is, to which of these classes this data point x belongs to, or classify this data point x to one of these classes, right? So what we are precisely trying to solve is, what is the probability of class Ck given data point x. So we want to classify this x into one of these classes, right? For that, what we be doing is, we'll be finding the probability of class C1 given x, probability of class C2 given x, probability of class Ck given x. So we'll be finding all those probabilities, and we'll be picking the probability which is maximum, right? We'll be picking the probability which is maximum, and to that class this x will belong to. So we are trying to solve this problem. Probability of class Ck given x, right? So that means we'll be finding probability of C1 given x, probability of C2 given x, likewise probability of Ck given x, and whichever will be the maximum value to that particular class, this x will belong to. If this is maximum, x will belong to this class. Maximum among all these probability, right? So and how can we find this? We can find this by using Bayes theorem. So let us write the Bayes theorem for this. So if I write the Bayes theorem for this, it will be probability of Ck given x is equal to probability of Ck into probability of x given Ck divided by probability of x. So that is the Bayes theorem applied on this term. Yeah. Now this was for Ck. If I write the Bayes theorem for C1 class, C1 given x, that will be equal to probability of C1 into probability of x given C1 divided by probability of x. Probability of C2 given x will be equal to, again by applying Bayes theorem, probability of C2 into probability of x given C2 divided by probability of C2. Similarly, we can write this formula for C3, C4, C5 for all the classes, right? The point to note, so what we are interested in, calculating this complete term, right? Then only we'll be able to know this value. We'll be computing this complete term, then only we'll be getting this value. Similarly here, and so on and so forth. But the point to note here is, if you observe the denominators of these terms, it is probability of x, here also probability of x, here also probability of, this is probability of x, it's not C2, it's probability of x. So here also probability of x. That means in each of the term, the denominator is same, that is probability of x. So why can't I neglect this? I can neglect this, right? So rather than comparing this whole term, I can compare only the numerators now. I can calculate only the numerator here, numerator here, right? So because the denominator is common, so I can neglect the denominator. So the term ultimately becomes, which I'll be computing in order to get the answer to this, is probability of Ck into probability of x given ck, right? So in fact, this equal to will be written like proportional to, right? Because now we are removing this term in the denominator. We are removing this. So this probability of ck given x is proportional to now, is proportional to ck into probability of x given ck. Similarly here also it will be proportional to probability of c1 given probability of x given ck. Sorry, c1, right? So on and so forth, right? So what I got is now probability of what I need to compute now is probability of ck given x is equal to, or is proportional to, rather proportional to probability of ck into probability of x given ck. I need to compute this for each of the class. I need to compute this, right? Okay, so further, let us further simplify this. Now what is this? From the definition of conditional probability, if I read the definition of conditional probability, it is like this: probability of A given B is equal to probability of A intersection B divided by probability of B. So if I simplify this, right, if I take this denominator on the LHS, I'll have probability of B into probability of A given B is equal to probability of A intersection B, and that's what precisely it is, right? So this is nothing but this portion, where of course A and B are different here. In place of A we have ck, in place of B we have x here. So, but if I look at from this formula, right, so this I can write as probability of ck intersection x, right? So, or I can write it as probability of x intersection ck, because this intersection operator is commutative. So I can write this either this x first or ck first, it does not matter, right? So ultimately my probability of ck given x is converted to probability of x intersection ck, right? So also I can write it like this: probability of x comma ck. This comma is nothing but the intersection operator. This is the style of writing in some books, right? So I can use this. That means my problem of finding calculating this boils down to this, right? Okay, so now let's try to understand what is this x. As I said, x is a data point. X is a data point, right? This x is a data point. That means it can be a n-dimensional vector. It can be x1. I can write x as x1 comma x2 up to xn. That means this x data point has n features. It may have n features, right? So for example, this can be understood from the thing like this. So let's say we want to predict the prices of the house. So that means we are giving house as input to the, of course this is a regression problem, this model, and this model will tell the prices of the house. But this house is nothing but x. This house is nothing but x. But of course this house will have some features. This house will have features. So those features are, let's say, the distance of house from the school, comma, distance of house from the market, distance of house from the, let's say, hospital, so on and so forth, right? So these are nothing but x1, x2, x3. That means for this data point, these are the features. So when you give these features as input, our model will predict the price. Of course, the problem which we are solving is a classification problem, but just to give you the idea of what is this x, how this x is n-dimensional feature or n-dimensional vector. So that example I give. So okay, having said this, now let us come back to our problem. Our problem has now become the problem probability of ck given x is equal to probability of x comma ck, right? That's what we have got. Now if I write this x as x1 comma x2 comma x3 up to xn, right, comma ck, we want to solve this problem. We want to find this probability, right? Now by using the conditional probability, if I assume this as my a, if this is my a, if this is my a, and if this is my b, so this is nothing but probability of a intersection b, this comma is nothing but the intersection operator here. So this is probability of A intersection B. So the probability of A intersection B by using conditional probability formula can be probability of A given B. So if I show you the formula, probability of A given B is equal to probability of A intersection B divided by probability of B. So I'm using formula for this, right? So this is nothing but A and this is nothing but B. So probability of A intersection B is equal to probability of we don't have A here, we have X's and CK. So probability of X1 given B, A given B, right? And I need to take this on the LHS, right? So then only I'll get formula for A intersection B. So X1 given X2, X3 up to Xn, comma CK into probability of B. And what is B? B is this term, probability of X2, comma X3 up to Xn, comma CK, right? So that's what I got. Again, if I apply the conditional probability formula on this term, this will be my A, right? And this will be B, right? So if I apply conditional probability formula on this term, I'm writing this term here, right? So I take this equal to sign here. So I will have probability of X1 given X2, comma X3 up to Xn, comma CK, this term, and then applying conditional probability formula on this term, I'll have probability of X2 given X3, comma X4 up to Xn, comma CK, right? Probability of A given B into probability of B. B is this term. So into probability of X3, comma X4 up to Xn, comma CK, right? Okay, now if you apply this formula again, intersection, this formula, conditional probability formula on this term will be expanded like probability of X3 given X4, comma X5, comma up to Xn, comma CK, right? So ultimately, if you go on expanding this term, ultimately what will you have? What will you have is, right? So let me write here probability of X1 given X2, comma X3, Xn, comma CK into probability of X2 given X3, comma X4 up to Xn, comma CK. Likewise, you will write for X3, and then finally you will have probability of Xn given CK into probability of CK. That's the term you will get if you go on expanding each and every term, right? Okay, so let me rewrite this on a new page. So what we have is probability of CK X1, comma X2, comma X3 up to Xn, comma CK is equal to probability of X1 given X2, comma X3 up to Xn, comma CK into applying the conditional probability the definition of this, you will get this term will become probability of X2 given X3, X4 up to Xn, comma CK, right? Applying the conditional probability definition on this, it will be probability of X3 given X4, so on and so forth. So ultimately this will be probability of Xn given CK into probability of CK. So that's what we got from this by applying simply the definition of conditional probability. Now, how will we solve this? How will we find this? Just to simplify this, let us try to understand what is the feature independence, right? Or conditional independence of the feature. So let's say we have this conditional probability definition. So here I'll write the definition. Probability of A given B is equal to probability of A intersection B divided by probability of B. But when A and B are independent, this will be probability of A into probability of B divided by probability of B. So this will get cancelled, right? And that means probability of A given B is equal to probability of A. Now, if I write probability of A given B comma C, right, which is equal to probability of A given C if A and B are conditionally independent. If A and B are conditionally independent, then I can write this as probability of A given B is equal to probability of A given C. So by applying this conditional independence of the features, I can rewrite this. So let me rewrite this, which is equal to. So let's say this is our A, this is B, and this is C. If this is A, this is B, and this is C. So if I rewrite this term, it will be probability of x1, that is A, given C. C is nothing but Ck, right? Similarly, if I apply this conditional, features are conditionally independent of each other, right? So this will be x2 given Ck, probability of x2 given Ck. Likewise, next term will be probability of x3 given Ck, right? And so on and so forth. It will be probability of xn given Ck into probability of Ck, right? That's what we get, right? So this is nothing but product of probabilities, right? So I can write this product like this. Let me make some space here. Okay, so if I rewrite this by taking the probability of Ck, this is Ck, sorry, this is Ck, probability of Ck. So probability of Ck out, if I take this probability Ck outside, then this will be product. Pi is nothing but a symbol of product. Pi, product of I is equal to 1 to n, probability of xi, comma, xi given Ck. So when I is 1, it will be x1 Ck, I is 2, x2 Ck, so product. So that's what we will be solving, right? So in order to find this, we'll be solving this, and we'll be doing this for each class C1, C2, C3 up to Ck, and for whichever class this term is maximum, the data point x will belong to that class, right? So that is how we try to find in naive Bayes classifier. So ultimately our problem boiled down to this. So in order to know this, we are solving this, and for each class we'll get this value, and for whichever class, whichever Ck, this value is maximum to that Ck, this data point x will belong to, right? So that is the naive Bayes classifier. And just to summarize quickly, I'll summarize quickly what we did, right? So what we are given, C1, C2 up to Ck classes, and we were given the data point x. And the question was to which class this data point x will belong to. For that, we found the probability of each class Ck given x, right? And for whichever class this probability is maximum to that class, this x will belong to. And for solving this, we use the Bayes theorem. Bayes theorem ultimately, we simplified it further, and we reached to a situation where we computed finally probability of Ck into product of I is equal to 1 to n, probability of let me show that term here. So this is the term, right? Probability of xi given Ck. So probability of xi given Ck. So ultimately we will try to find this term, and these probabilities will be given to us. So thus naive Bayes classifier classifies the problem by extensively making use of the probabilities. So it's a probabilistic classifier. So I hope you understood this, and please stay tuned to watch more videos on data analysis, machine learning topics. Thank you very much.